it's the streaming is started already. So what we're gonna do today, which is this is how this is how I have been lecturing since the beginning of this semester. Is really just kind of go by the topics in Canvas. So when you see a link, that's basically those are the reading material, and I'm just going down sequentially, unless I make a mistake and forget that, oh, I haven't I haven't really finished basic set theory, and then I jumped onto basic quantifiers because I forgot that I did not quite finish the last portion of the first link. But other than that, okay, unless I make a mistake like that, it's just really sequentially following the links in Canvas. So in case anyone is wondering in the future, what module we'll be talking about next, it's just whatever is down the list from the modules in Canvas. So there's that. All right. So I'm still waiting for maybe another 3 minutes or so. But if you guys have any questions, you can go ahead and ask questions, because since I'm here already, might as well answer some questions. If you guys don't have any questions, I can tell you what the professors are thinking about doing these days. We are thinking about offering classes in high flex format. So high flex is basically a hybrid, with flexibility, and therefore the name high flex. It's a combination of synchronous and asynchronous online class with face-to-face options. Yep, mix all of those things together, and you get high flex. So the idea is, let's just say that I'm teaching this class and I'm on campus. Okay, so I'm basically just, I can be teaching this class exactly the way I'm doing it right now, except I'm in a classroom, okay, with face-to-face students in the classroom. So that's called SyncFlex, okay, which means it is a synchronous online class combined with a face-to-face option for people who want to show up in the classroom. They can show up in the classroom. All right, so do we have infinite attempts to take a quiz? Well, frankly, I do not remember. I do not remember, but let me see if now I know that you have until next. So basically, this is the same kind of instruction that you should get, when you take the test. I guess if a test is allows an infinite number of attempts, it would show up here. I'm not really sure, but the bottom line is, well, you have until next Wednesday, at noon, to turn it in. So whether you can, I really don't think people should be, using the infinite number of attempts, because that seems to suggest that people are going to use the trial and error approach, which may not be the best way to learn. So, but I still don't remember. I suppose I can just try it out, right? Take the quiz, and let's see. It doesn't say anything here. Alright, so I'm just going to submit an empty quiz with no answers whatsoever and see if I can take it again, right? Alright, so I got 0 out of 10, not surprising. And let me see if I can take the test again. Alright, so I don't think so. I don't think I set up this one to be like that. So I go to set theory again, and it does not give me an option to take it again, which means you do not have an infinite number of attempts to take this one. But there's no time limit. So given there's no time limit, I'm hoping people do not need to rely on having an unlimited number of attempts. So there you go. Alright, so we got about 30 seconds before the class starts. And Nathan is typing something. Well, I mean, it's up to you guys, right? I mean, you got a whole week to schedule how you want to use it to answer these questions. And as long as you're not submitting, you can still go back and change the answers. And that's the idea, is not to rely on the unlimited attempt thing, to basically just go like, oh, if it's not this answer, let me try the next one, try again. Nope, it's not that one, let's try the next one again. Nope, it's just like spend the entire week, okay, just thinking about it, absorb it, just kind of chew on the concepts, maybe ask some questions in class in order to figure it out. Yes, so Danny, you can indeed start an attempt. As I think you have to do some activity in order for your answer to be recorded by Canvas, but as long as it is recorded, you can basically throw your computer under the bus, roll over, kill the computer, buy a whole new computer, okay, set up everything else, sign back into Canvas, and it will let you continue the quiz. So there you go. Yeah, but I do not suggest people to actually throw their computer under the vehicle and roll it over with. I was just saying that even if that happens, you can still continue with your quiz. Yeah, I have to make sure that people do not misunderstand, because some people may listen to only a part of this conversation and go like, oh, so Tech told us to roll over our computers with a car. No, that is not what I was suggesting. I was simply saying that, yeah, you got a lot of options. Alright, so we'll start with a little bit of nagging. That's what parents do, and I am a parent, not to you, but to my kids, right? So I have this habit of quote-unquote nagging. I know nagging is not effective, but a reminder is effective, right? Sometimes, from time to time. And let me go back to the tab here. And I'm gonna cross this out and change it to a little reminder. There we go. Alright, so I'm going to assume everybody in this class is spending the recommended amount of time outside of lecture time to review the material, to study, to do the homework, to think about the concepts, okay? And that amounts to 320 minutes a week. Yeah, 5 hours, 5 1/3 of an hour. That is how much time people are expected to spend outside of a lecture to review the content, do the homework, just to understand the concepts and so on. Does it sound excessive? No, I don't think so. Because some of that time you can probably be doing something else. I personally would do something like I would read something that I need to understand, and then I will remember all that stuff. Well, I don't need to actually explicitly remember that stuff. I'll read it and I'll think about it a little bit, and I'll go do something else. Your mind, actually does a lot of processing in the background, so even when you're not actually reading something, as long as it is on your mind at some point in time, your brain is still working on it. So I would say these 320 minutes is going to include that time. I have to tell you that when I study, when I quote unquote study, most people look at me and go like, Tech, you're goofing off. No, I'm not goofing off. I'm actually studying. I don't see you studying. There's no book, there's no notes. You're not doing anything except you're just sitting around listening to music. Yeah, that's how I study. Alright, so I'm not going to get into how to study, because I just gave you the amount of time. But how do we study? I have some material prepared, actually written, in the winter break. So for anyone who is interested, I can share that material. Okay, I can share what I understand as studying, and at least it was effective for me. Doesn't mean it's gonna be effective for other people. Where's the homework? I just clicked on it. So maybe paying attention can help a little bit. I think that that really is one of the most important thing. And then the other thing is everything is recorded. I'm just checking. YouTube is indeed recording. So that means everything that I'm doing on the screen is being recorded, unless I'm doing something over here that is under my own face, then you cannot see it. But most of the things that I do, like clicking on the homework, which is here, that is recorded. So I highly suggest people to, one, actually be present in the lecture, in the synchronous lecture, and two, make use of the recording, because that is actually a resource that you guys can count on. Yeah, that's it's in the form of a quiz, except it is not due until next Wednesday at noon. And that was exactly what I was illustrating like a few minutes earlier. Alright, so now that I'm done nagging / reminding, we're now getting back to the class material. So we're going to continue to talk about set notations, but this time we're going to use quantifiers to help clarify some of those concepts. So we are now onto this module over here, and I'm just going down the list. Okay, you see a link, 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 and then the next link is down here. I'm also hoping that people can read ahead of time. That's also a effective way of getting ready for a lecture, because now your mind has some idea of what is going on, and I'm just filling the details during the lecture, so things can sink in better when people read ahead of time. But since I'm not in control of the action of other people, so every person gets to decide how that person wants to get things done. That's a freedom for people to use. Alright, so now we are going to get into set theory using quantifiers. Alright, so here we go. You can see the timing is actually about the same time last year, so that means I'm kind of on schedule right now. So the rationale is, although basic set theory was already discussed in the previous module, which is 0280, which I think I can assume everybody to have read at least once, if not several times. Then we talked about the use of quantifiers. So quantifiers are very useful for a variety of math topics. All of you have taken pre-calc, okay? At least pre-calc. And calculus uses quantifiers, because the whole idea of taking the limit of something, the whole idea of the first derivatives is based on quantifiers. Okay, there exists an epsilon that is greater than 0 such that blah blah blah. I'm hoping you still remember that stuff, because that really is the essence of calculus. Okay, that's the very foundation of calculus, is taking the limit of something. So that can be expressed using quantifiers. And what we're going to do is we are going to use quantifiers to revisit some of the concepts that we have already talked about. The first one is really important. How do we establish the equality of two sets? Okay, so if you're given two things, one is called x and one is called y, how do we know they are the same? Well, first of all, if one of these is a set and the other one is not, then we know for sure x equals y has to be false. In other words, they have to be of the same type. So if one is a set, the other one has to be a set also, in order for these two things to be the same. Now, given that x and y are both not sets, then you can just use the normal comparison. So if it's numerical, use numerical comparison. If it is a string, use a string comparison, and so on. On the other hand, if both are sets, then we're going to use this notation here. So x equals to y if and only if, and then on the other side we have for all e in x, e is in y, and for all e in y, e is also in x. That's how this particular mathematical expression is read. Do we have any questions about what I just said? All right. Oh, okay, very good. See, Danny just saved you guys, the trouble of hearing my little crickets, sound effect. Because if Danny had not responded, I would have played the sound clip of crickets. All right, moving on to the next one. Yes, I found it. Okay, I misplaced this little thing, earlier, and now that I have found it, I'm planning on using it. You'll get it. You will hear it. Okay, so there's another way to define this. It's more concise. So the more concise way to do this is to say x equals to y, given that x is a set and y is also a set, if and only if, and then there's a for all. So this for all, okay, for all e, is referring to everything in the entire universe. Okay, so it's not limited only to things that are either in x or in y. It is everything. So considering that we are looking at everything in the entire universe, we are evaluating this expression here, which is a if and only if expression. So the if and only if expression says e is in x if and only if e is in y. So that means, if we're talking about something that is not in x and not in y, not a problem. Okay, if I pick something that is not in x and not in y, then the if and only if is going to be true, because if both sides of if and only if are false, the if and only if is guaranteed to be true. So do we have any questions about how these two notations are really expressing the same thing? It's just that one is a little bit more cumbersome and the other one is, well, I mean, in a way, more simple. And yes, I'm quite ready to use this. There you go. So I think having those sound effects are important. Alright, so what does the upside down A represent? Yes, it does. We have been using this for at least 2 classes. Yes. Yep. There are some crickets. But they are certainly not my conscience. I think I misplaced that a long time ago. Alright. Alright, cool. Yeah, absolutely. I'm just double checking in the text channel. Everything is okay. Yep. So Philip, you are correct. The upside down A is indeed the for all. Now the other thing you can also do, okay, because I'm hoping that you guys have this document open as well, because if I'm the only one having this document open and I'm doing the screen share, then I'm driving the bus, right? I'm just scrolling, back and forth, until you guys are dizzy. On the other hand, if you also have it open on your side, then you can stay at one place and you can then do all kinds of stuff. For instance, you can right click on it, go to show math as, and then just kind of look at how the tech command is entered. And once you do that, you will realize that, yeah, oh, that symbol is indeed called for all. So there are also all kinds of little things that you can do here. If you have been using Joplin to take notes, Joplin takes the same kind of math notation as what I used to create these modules. So you can basically just copy and paste into Joplin. As long as it's within $2, it's gonna work. So that means you have ways to take notes. Like if you don't want to spend the time to actually hand type something that is in my notes already, you can just copy the notation and kind of slap it onto your Joplin notes, and it's there, right? Okay. Let's see. Yeah, so there exists is the E thingy. We are seeing it down here. So this little E thingy exists. That's the other quantifier. That's the existential quantifier. And that's why in one of the row-taking activity, I used the 2 words existential crisis, right? And then some people copied both words as the answer, even though I said you only need one of the 2 words to be the answer. I remember that. Alright, so next. So we try to describe what is in a set, okay? And this time we are given a predicate as a criterion of, what qualifies as an element in this particular set. So when we use this notation, it'll be the same thing as this notation here. In other words, when you read E equals to open brace x such that P of x is true, close brace. So this is one way to read this, but it means exactly the same thing as this notation over here, which is if you examine everything in the entire universe, this whole thing has to be true for everything in the entire universe. X in E if and only if P of x is true. That is meaning exactly the same thing as this definition over here. Basically, we're saying, if P of x is true, then x has to be in E. On the other hand, if x is in E, then P of x also has to be true. So it's an implication going in both directions, and that's why you see the if and only if operator here instead of going in one direction. Alright, so we got a question in the text channel just to confirm the shorthand x such that x is in x is a shorthand for an implication. You mean here? Oh, I see. That's a tricky question to ask, because it depends on the quantifier. In the case of a universal quantifier, yes, it is an implication. In the case of an existential quantifier, it is a conjunction. It's basically a filtering mechanism. When you look at that notation, it's a filtering mechanism, which basically means if x is not something in this particular set of things that we are interested in, just make it true so that we don't have to worry about it, or just make it false so that we don't have to worry about it. So if you are working with a for all, the quote-unquote default value for something that is not in the set of things that we are interested in, the default answer should be true. Because with a universally quantified expression, everything is true unless it is proven wrong or false. On the other hand, in an existential quantifier, it is the other way around. Okay, the default should be false because if we find one thing of the entire universe that makes the predicate true, then the existential quantifier becomes true. So in that case, if you're considering something that is not in the set E of things that we are interested in, then the default answer should be false so that we don't accidentally make the existentially quantified expression true. So that is that. I think we kind of talked about this last time as well, but these material kind of takes time to absorb. You kind of have to look at it from different perspectives, and not really sure how to teach that. Okay, which I think is very important, is to look at things from different perspectives. Try to think of as many ways as possible to look at the same thing. All right, next thing up is the empty set. So how do we know that S as a set is empty? Well, this statement has to be true. So what this statement is saying is it is not the case that there is at least one thing in the entire universe such that that thing is in S. Yes, it is a very long and cumbersome way to say that S as a set does not contain anything. It is an empty set. But since the main idea of this particular module is to utilize quantifiers to revisit some of the concepts that we have looked at already, this is how we can use it. This is how we can use a quantifier to basically say exactly the same thing. Now, if you remember, we can also move the negation to the inside. But when you do that, you have to change the quantifier. So it changes the existential quantifier to a universal quantifier. So that would basically be saying for all x, x does not belong to S. X is not in S. That would be saying exactly the same thing, that S is an empty set. So are we good so far? All right, cool. And then we have unions and intersections, and you can basically see that they are pretty much the same thing, except we just slap on a for all x on the outside. So this way it is it's clear that we are not dealing with an existential quantifier to basically say, hey, of the entire universe, if we find at least one thing like this, that makes the quantified expression true. No, we are using a universal quantifier, which basically means no matter what you pick, of this entire universe, we better make sure this entire expression here is true for that one thing that you're considering. But that one thing can be anything within the entire universe. So everything in the entire universe has to make this entire expression true. And then for union, it's kind of the same thing, except we are changing the intersection symbol with a union symbol, and then we're changing conjunction with a disjunction. So that's the only difference between intersection and union. All right, moving on to Cartesian product. So with a Cartesian product, we have a nested universal quantifier. For all x in A, for all y in B, we want the following to be true. So what is the following? So the following is to say xy is an element of A Cartesian product with B, and for all xy in A Cartesian product and with B, x is in A and y is in B. So with this one, the difficulty is going to be kind of tracking the level of parentheses. So we have one, okay, this entire side here, okay, this entire side here is one statement. This is a conjunction, and this is another statement that is also universally quantified. So the reason why there are two is because we want to say, hey, if you just pick something from A and pick something in B and make a tuple out of it, that tuple has to belong to the Cartesian product of A and B. On the other hand, if you pick something from the Cartesian product of A and B, you better make sure that the first thing in the two tuple can be found in A, and the second item in the two tuple can be found in B. So you need to go in both directions. So the Cartesian product cannot contain anything in addition to two tuples where the first item comes from A and the second item comes from B, and it cannot be lacking any one of those items either. So that's why it is expressed in this particular way. There are probably other ways to express the same thing too, but this is just the one way that I thought of when I was typing these notes. All right, so last one would be the subsets. So A is a subset of B if and only if for all elements of A, that element has to be in B as well. And then A is a proper subset of B. It's basically saying A is a subset of B to begin with, and there exists an element in B that is not in A. And that's it. Just a slightly different way of looking at the same thing. And that's it. This is the basically revisiting the concepts of set operators and notations, but this time we are utilizing the quantifiers. The universal quantifier, the for all, with the inverted A, and the existential quantifier, which is the E that is flipped on the horizontal axis. So do we have any questions before we move on to functions? Yep, I hit a button before Danny replied. Danny was probably typing on the keyboard, thinking, "Oh no, I'm taking a little bit too long. The cricket is coming." Yep. Well, it's very easy. I intentionally make it so that it's right here, resting on my half mirror setup. I should probably just kind of glue it there if it's if this thing did not have a battery compartment that is on the back side of it, I would have just glued it. Well, I can actually solder wires to bring the battery connection outside. Then I can actually glue it down. Okay, something to do after the class. Alrighty. So we are now done with the set notations using quantifiers, and we are now moving on. So when we are moving on to functions, and functions are, there are two main modules. One is basically just asking what is a function, and then the next one is basically saying, okay, given a function, what do we know about a function? What are some of the attributes that we can qualify, for functions? So first thing first, let's go consider what is a function. So there we go. And the first thing we talk about is a tuple. But we talked about tuples already when we talked about the Cartesian products. So in order to describe a function as a set, we need to utilize the concept of tuples. And here's a link, back to the original module that talks about, tuples. I try my best, to kind of contain back references, to modules that are basically prerequisites, to the current module. So this way, people can just kind of go back and go like, oh, okay, I kind of, not remember what a tuple is. They can kind of go back to check that out. So a tuple in general is an ordered container where its components are ordered and the ordering is significant. So when you have a tuple of, here's an example. The tuple, this is a 3 tuple because it has got 3 things in it. So the 3 tuple 112 is considered distinct from the tuple 121, which is also distinct from the tuple 211. So it's illustrating quite a few things right here. Okay, with a set, you cannot have 2 ones in a set, okay, inside the curly braces, because every element has to be unique in a set. But a tuple is more like an array. Can you have 2 elements in an array having exactly the same value? Absolutely, right? So that's why I use this specific example where we have 2 values or 2 elements of the same value, and then we also have one that is different, so that when we move the position of the element that has a different value, we consider those tuples to be distinct. Okay, so this tuple is different from this tuple over here. A tuple is represented by a comma-separated list of items enclosed in parentheses, and so on and so forth. So we kind of talked about all of this stuff already when we talked about Cartesian products. Do we have any questions about the notations of a tuple, what it means and how a tuple is different from a set? Any questions about those? Okay. Doesn't seem like there are any questions. And I can even use JavaScript, as a function to tell you how to compare the equality between 2 tuples. I mean, that's actually pretty easy to do, and it would be very similar in terms of the syntax compared to C and C++. And since nobody cared about that, we're going to move on to functions. Alright, so we learned functions in other math classes, okay, because you guys have all taken pre-calc, so I'm fairly sure that the concept of a function was already introduced in Math 370 or Math 372. So those 2 classes are basically the same. In C++ notation, how about this? I will do it in JavaScript, because JavaScript has certain things that make it very convenient, whereas in C++ it doesn't really have the same features. All right, so this is going to be in JavaScript. This is why I like Markdown, because it's easy to kind of throw in a function. So I'm going to say function tuples. Let me change from dark mode back to the usual. So I'm going to say tuple eq for equality, and we'll have t1 as a tuple, t2 as a tuple. So JavaScript, unlike C++, is not a strongly typed language, and as such, it doesn't need types when you are declaring parameters or local variables. So now the first thing we want to do, so I typically do not like to do a return inside a conditional statement. So I have a local variable called result or return value, depending on how you want to name it. So it can even have a default value. So let's just say that by default, we say the answer is false. Okay, so unless we can confirm the answer is true, actually it's easier to do it the other way around. So I'm going to say by default it is true. So until we can find a reason to say that the tuples t1 and t2 are different, we're going to return the default value of result like that. Alright, so the first thing we need to do, I'm not going to do type checking. In other words, I'm assuming that T1 and T2 are indeed tuples or arrays. So I'm not checking it. You can check it if you want to. It's just some extra work, and it's not really important in terms of the illustration of concepts in this class. So I'm not going to check the types of T1 and T2, and I'm just going to assume that both are tuples or basically arrays. So the first thing I'm going to check is, do they have the same length? Like arrays in programming, this class start indexes with 0, not 1. COBOL, Fortran, and Visual Basic. Don't forget Visual Basic. Yeah, Visual Basic also use, in certain things it is 1 oriented, and other things it is 0 oriented. Alright, so the first thing we're going to check is, does T1 have the same length as T2's? Because if they do not have the same length, guess what? I'm not going to bother to evaluate or to check the content, because they cannot be the same. So we just say result is false, because we found a good reason to say nope, they are not the same. So on the other hand, if they do have the same length, what are we going to do? Well, we have to go through every single item in the array and make sure that each item of T1 has the same value as the matching item at a matching position of T2. So this is the really important part of how we compare two tuples. So I'm going to use JavaScript in this case, but I think most of you can understand this syntax already. So I have a local variable I that is locally declared within the for block, and I'm going to check whether I is less than t1.length, and if so, we got something to do. Otherwise, we increment the pointer, increment the index. So in here, I'm not going to optimize the code in any way. I'm just going to make it so that it is it's just making the point. Okay, so result is result and t1 bracket I equals to t2 bracket I. In other words, once result becomes false, it will stay false. Okay, so this loop is not really exactly optimized, because I can take an early exit as soon as result becomes false. But I'm not going to do that, because that's not the main point of this illustration. All right. Yes, so triple equal to also checks the type. Yes. And the type, in JavaScript, there are certain things that can be a little bit confusing to people who program in C or C++. Such as in JavaScript, there are two different values. One is called undefined, and the other one is called null, and they are not the same. So I'm not going to get there. Okay, I'm not going to talk about that. I'm just going to be assuming that we have basic equality. And I think what Chandra is referring to is the comparison over here can be a triple equal to. Now, I'm not really sure whether I want to have a triple equal, because with a triple equal, if two strings have exactly the same content, but they are from different places, are they still considered triple equal to in JavaScript? I'm not sure about that. So I think I'm just going to settle with double equal to, so in this case, double equal to will work in most cases. It's going to work for numerical values, characters, and strings. It doesn't work for objects, and it doesn't work for arrays, because those things, you can compare the references of those things using a triple equal to, but a double equal is going to basically not be able to do that. So I'm going to just use a double equal over here. So other than that, okay, does everybody understand the logic of this code, even though it is written in JavaScript and not C++? I mean, the syntax is really similar to the syntax of C++, and the main reason why I use JavaScript instead of C++ is C++ doesn't have this. In other words, an array in C and C++ is really nothing more than a pointer. You really have no idea of how many things are in an array unless you use the template class of array, which then brings in a whole bunch of extra code and extra runtime stuff that we don't really need to deal with. All right, cool, excellent. So there's that, and now we are moving on to, okay, let me close this. There we go. So now we are moving on to, okay, then what? So in your other classes, we learned that you can define a function. So if you want to call a function f of x equals to 2x is one kind of really standard way to define a function. So this way, if we say, what is f of 2? Well, f of 2 is 2 times 2, which is 4, and so on. So this is the normal, usual way for mathematicians to define a function. In this class, we are looking at a function as a map that maps elements from a domain set to a codomain set. In some other math classes, the word range is used instead of codomain, but in this class, I'm just going to use the word codomain to refer to the destination set of where things are mapping to. When we describe a function in this class, it is important to identify the domain and the codomain. So this is a notation that we'll be using all the way through to the end of this entire semester. So you probably want to get used to it. You probably want to kind of stash this definition somewhere so that you have all the definitions neatly tucked away in one place. So whenever you need to look up a definition, that's that one place that you just need to go to in order to look up a definition. So in this definition, f is a function. So this notation does not apply if f is not a function. Then we don't use this notation. So whenever we use this notation, we are already assuming that f is indeed a function. And later on, we'll talk about the qualifications of what it takes to become a function. But the most important part here is x, which is on the left-hand side of the arrow, identifies the domain. So x has to be a set, and it becomes our domain. And y is the codomain. So the arrow always goes from the domain to the codomain. Do we have any questions about this particular notation? Now, obviously, right now, we have not yet defined what is a domain versus a codomain. I'm simply saying, by position in this notation, we can identify which one is the domain and which one is the codomain. Okay. So both x, yes, and indeed all three are sets. F is a set, x is a set, y is also a set. So they are all sets. All right. Okay, so in this class, unlike your other classes, math classes, we view a function as a set. Indeed, we view a function as a set of two tuples. So what we're going to do is I'm going to show you an example. Okay, so I'll show you an example of f of x is 2x, but we specifically want to use the set of all integers as our domain as well as our codomain. So this funny looking z here is the symbol for the set of all integers. So in this case, I am basically telling you that we have a function f where the domain is the set of all integers, and then the codomain is also the set of all integers. So if we want to do something like this, okay, if we want to define f of x to be 2x, then this is going to be one way to look at what is inside the set f. So f consists of elements. The first one element is 0, 0, which means we are mapping 0 to 0. The next one is 1, 2. We are mapping 1 to 2, and then we have 2, 4, which is mapping 2 to 4, mapping 3 to 6, and then obviously on the negative side we should also have -1 mapped to -2, -2 maps to -4, and so on. So do we have any questions about how we are looking at a function like a map, and then we are looking at a function also as a set, where each element of the set is telling you how one element from the domain maps to an element in the codomain? Are we okay with that concept? Alright, cool. So we are running into a problem that we have talked about before. Oh, Luke has a question. How is the codomain all integers if it's impossible for the domain to map to some integers in the codomain? That's a very good question, because it is actually okay not to map to some of the elements in the codomain. That's perfectly okay. Let me give you a very extreme example of something that doesn't really map to a whole lot of elements in the codomain. So I'm going to use this to illustrate that concept. Alright, so I'm going to say consider, let's not use f because we are using it already. We can use h for now. So h is a function. It maps once again from the set of all integers to the set of all integers as well. Alright, and I'm going to give you a sample of the content of h. So in math, we define h of x to be 0. That is a function. You can indeed define a function where it doesn't matter what the parameter is, it just returns a 0. Okay, because remember, a function in math is essentially something like a function in C programming, where you just have to take the parameters and go like, okay, I might be doing some processing with the parameters and then come up with the return value. So in this case, h of x is kind of analogous to this JavaScript function definition here. I mean, this is not a surprise to anyone, because all it does is simply to return a 0 all the time. Okay, but how do we express this, right? As a set. So as a set, h is basically mapping 0 to 0. It's mapping 1 to 0. It's mapping 2 to 0. It's also mapping -1 to 0, -2 to 0, and so on. And that's perfectly okay. H is still a function. Alright, so we'll later on, depending on how much time we have today, but later on, I will describe, exactly what it takes to call a set of two tuples a function, given that we already know what is the domain and what is the codomain. Well, this is perfectly okay. Having the set of all integers as a codomain is perfectly okay. And having the set of just 0 is also okay. Because the rule doesn't say anything about that everything in the codomain has to be mapped to. It simply says, well, if you want to map to something, that something better be in the codomain. But it doesn't mean that you have to use everything in the codomain. So there are very specific words that we'll talk about later on, the terms injection, surjection, and bijection. That has to do with, Are we mapping to everything in the codomain? Are we mapping to only certain items in the codomain? So there are two words that relate to that. So we'll get to that, when we probably sometime next week. I think we'll spend the rest of today, just to look at the qualifications of what makes a function a function. All right, so this is just an example, where you can have a funky function that maps everything to a single element in the codomain, and your codomain is huge. It's okay, perfectly fine, not a problem. All right. So what we are also going to do here is to say, okay, if I want to use the function that was earlier defined as f of x is 2x, but we also want to use the set of all integers as the domain and the set of all integers as the codomain. But we don't want to write it out like this, because who knows what these ellipses are basically representing, right? So we have to use a more precise way to say what is in the set. Yeah, sure. Yeah, you're welcome. So the way to do this is to use this notation. We have used this notation already. And this notation works like, okay, every element in F is going to be a 2-tuple in the format of some x and then twice the value of x. And then the vertical bar is such that x has to be an integer. And that's the only restriction. As long as x is an integer, we make two tuples where the first item is just x and then the second item is twice the value of x. All of those items are in F. So we are basically reusing some of the concepts that we have previously mentioned. Just curious, JavaScript doesn't have comma at the end of each line? No, it is not a comma. At the end of each line in C++, it is a semicolon that is at the end of each line. And you are correct, JavaScript does not need a semicolon. You can give it a semicolon, it doesn't complain about it, but it doesn't need it. Alright, so now that we have answered the question about JavaScript, well, you can in JavaScript it is optional. Okay, so in JavaScript, if you put a semicolon here, 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 and also here, it won't complain about it. But if you don't have a semicolon, it's not going to complain about it either. There you go. Well, the problem with JavaScript is, in the absence of a semicolon, because it doesn't need a semicolon to conclude a statement, sometimes you would do certain things and you think it's going to do one thing, but it doesn't do that thing that you think it's going to do, which is problematic. Because with C++, until it sees a semicolon, it knows whatever is continuing on the next line is a part of the previous line and is part of one single statement. In JavaScript, when it gets to the end of get to the end of line, it goes like, can this possibly be the end of what is on this line and can be considered a statement on its own? If it can, it is considered a statement. So sometimes, if you intend to specify something else after that, and you separate it into two lines, it's not going to work the way you think it's going to work. Since I'm just mentioning this, I might as well give you an example. I know this is not a JavaScript class, but nonetheless, actually I don't have to go too far. I can use one of these things. So let's just say that this 0 here is on the next line, like so. That changes h completely, because now h is returning something, but it's not returning a specified value. Because return by itself is a statement. So by the time the interpreter is at the end of this line, it's asking the question, can this be the end of a statement? The answer is yeah. And then JavaScript just goes like, okay, cool, I'm just going to return without specifying a return value. So that's one of the things that is kind of bothersome about JavaScript is, when you are used to breaking a statement into multiple lines, you better make sure the last symbol of one line suggests to the interpreter that I'm not done yet. Okay, there's more to come. Please read on. So I have stepped on this one personally, and that's why I learn from it. The idea is not to make mistakes. The idea is you make mistakes and you learn from it. Hopefully once. Alright, so let's move on and talk about okay, if that question is directed to me, do I like JavaScript better than C++? The answer is yes. Because I'm one of those people where I like to prototype things really quickly, and JavaScript allows me to do that because objects can be constructed out of thin air. You don't need a stinking class to make an object like in C++ or Java. You just say I'm gonna create an object like this, and then later on, as the object is kind of floating around in functions and whatnot, if at one point in time you go like, I think this object can make use of a member function, a method like this. You can just go ahead and add it to the object, and then later on, if you say, "Nah, I don't think we need this method anymore," you can get rid of it. It's all in runtime, which makes debugging a program and also validating the correctness of a program a little bit of a chore, unless you use TypeScript, which is a compiled or it's a specification of JavaScript where things are typed. Yep. There we go. All right. Okay, so getting back to the main topic here. Sorry about the digression. So right here we are basically, this notation here is going to be saying the same thing here. For all x in Z, for all y in Z, y equals to 2x if and only if xy as a 2-tuple is in F. It's basically expressing exactly the same thing. Alrighty. For those of you who don't know what is TTP ASM, TTP stands for Tax Toy Processor, which is the architecture that I use in CISP440. So TTP ASM is basically my own assembly language that is compiled or assembled to opcode that is specific to my own processor, which runs in Logisim. So it's kind of like one of those plastic engine model thing where it is transparent. So there's a tiny little crankshaft here where you can crank it and you can see all the valves in the opening and closing and the pistons going all in up and down like that. It's kind of like that. It basically gives you a view of what happens inside a processor when it runs. There you go. All right. So now we are on to section 3.1, which is where the heavy duty stuff is. Okay, so now I better not digress anymore, because earlier it's kind of like yeah we kind of know that stuff already. F of x is 2x and we have a new notation to express the same thing. Okay, now we kind of have to focus and concentrate. So what exactly does it mean when we have a function? And here comes the digression of taking roll. Good thing it comes right at this time before I really kind of get into the details. So let's get the roll taking thing done first. So I'm gonna have to do that and then go back to here and then find the roll taking activity for today, 0202. And there we go. So let me unhide it first so that you guys can refresh Canvas, just to be ready to answer the question. I just changed the answer to the question today, and I cannot remember what I changed it to. And the answer is onto. Okay, so I'm going to copy and paste it. So onto is one type of function that we are not going to get into in today's lecture, because there are several ways where a function can map things from the domain to the codomain, and onto is one of those. So there you go. Just copy and paste it, and you should be good to go here. And you guys, I think you guys have until 1:05, to enter that one word. So even if someone has to go to the bathroom, there should still be enough time. Yeah, you could type it, but when people type things, they sometimes unintentionally change the case, uppercase, lowercase, and stuff like that. So that may not be. Just copy and paste it. Then everything is guaranteed to work. All right. Yep. Yep. Copy and paste. All right. So we're gonna get into the first. Yeah, if you're using a mobile device, with a aggressively correcting keyboard, that may not be helpful either. All right, so we are now going to talk about the first requirement of what makes a function a function. So the first thing is, if you want to know whether f is a function, the first thing you need is to know, okay, so what is its domain? All right, so the domain is x. What is the codomain? The codomain is y. Now, can x and y be the same set? The answer is yes, they can be the same set, but they don't have to be. So the first requirement in order for f to be a function is simple. It has to be a subset of x Cartesian product with y. So that's the first requirement. If f contains anything outside of x Cartesian product with y, then f cannot be a function with x being the domain and y being the codomain. So this is the first requirement. Pretty simple, because all it means is whatever f has got to be elements of the Cartesian product of its domain and the codomain. Okay, so first requirement. Not too hard to understand and not too hard to check. So another important criterion for a function is not only does it need to be a subset, we also need to enforce this statement here. So I'm gonna just read it out here. So this is how someone might describe it using English, and it is each element of the domain must be mapped to one and only one element in the codomain. So when people read this sentence, they might say, "Oh, I understand every single word of the sentence. I'm good." Wait, hold on a second here. Okay, so let's check the statement again and make sure that we really understand this particular statement. So the first one is each element of the domain, blah 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 blah. Okay, but just this portion here is already telling you that we are using a universal quantifier. Every time you use every time you use each, you are implicitly saying, okay, we are using the universal quantifier for all. Okay, so we have to go through every single element of the domain and make sure that this other requirement here is satisfied. Okay, so that's the first thing. The second one is must be mapped to one and only one element in the codomain. So codomain is easy because it's part of the notation. Y is the set representing the codomain. Not a problem. Map to, yeah, we kind of understand what map to means, because all that means is the second item of a two tuple of an element of f, has to be satisfying this requirement here. So those are not the problem. The one thing that may be a little bit harder to catch is one and only one. So let me give you some examples. I'm just looking at the time, just to make sure that I'm not gonna end this class, with a cliffhanger. All right, so I'm going to give you an example. We'll consider x as the set of ABC, okay, and we'll consider y as the set of 1, 2, 3. There we go. All right. And I'm going to give you some scenarios of what f we want to evaluate, and then you can tell me whether the requirement that I have just mentioned is satisfied or not. Okay, so I'm going to give you the first one, having a1, a2, and then b3. There we go. All right. So let's take a look at this particular example here. If we define f like this, can we claim that this f is a function mapping from x to y? And if yes, then you don't have to explain any further. If no, you have to tell me why it is not the case. Okay, very good. Okay, so you guys are getting the idea of, no, this one doesn't satisfy the requirement, but why is it not satisfying the requirements? A is mapping to 1 and 2. All right, yes, so that's one reason, but there's another reason. And then Enzo says, no, because A maps to 2 codomains. Now, technically speaking, there's only one codomain, but it maps to 2 different elements of the codomain. And the rule so far, we have discussed it. It actually does not disallow that. So with what we have discussed up to this point, why is this particular f not a function? It's missing element C. Exactly. Okay. So A is mapping. Okay. So I take it back. Enzo was right. Okay, Enzo was right, but the terminology can be refined. So instead of saying no because A maps to 2 codomains, you can say it's better or more accurate to say that element A from X is mapped to 2 different elements in the codomain Y. So that would be a much more accurate way to describe why. One reason why this f is not a function. But the other reason is valid as well, is that C, which is in the domain, does not map to anything. So it breaks the rule. It broke the rule of every element in the domain must map to blah 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 blah. Okay, because C is an element of the domain, and yet it doesn't map to anything in the codomain. So there are 2 reasons why this f definition is not a function. All right, so let me just kind of emphasize that this is not a function. Is not a function. And I'm going to separate this into the 2 subcases where each one is also not a function, but focusing on only one aspect of why something is not a function. So I'm going to break it out. So the first one is simply to remove this extra element here. This is still not a function. Okay, this is still not a function because C does not map to anything. And then with the last one, I'm going to remedy it, in a certain way, but it will still make it not a function. So I'm going to say, okay, fine, you complain that C does not map to anything. I'm going to make C map to something. Are you happy now? The answer is no, I'm not happy because A is still mapping to 2 different things. So at this point, this is not a function only because C does not map to anything. This one is not a function only because A maps to 2 different things in the codomain. So now we can isolate a single specific reason why the f is not a function. Whereas the first test case, the first example, has 2 reasons for f not to be a function. Now obviously for something not to be a function, you just need at least 1 reason, right? You don't need 2 reasons for f not to be a function. But these 2 subcases here isolate exactly why in these 2 cases why f is not a function. All right. So we have the next one in the text channel. So I'm going to throw that in also. All right. So I'm going to put an empty line here And then I'll take away the stuff inside the braces, and then use what Miriam has entered in the text channel. There we go. Alright, so now what do we have? So we see A maps to 3, B maps to 1 and 2, and 3. C also maps to 1, 2, and 3. So this is not the function because when you look at B, it maps to multiple things in the codomain. It breaks the rule of one and only one. And that's why it's very important to understand what is one and only one. It means it cannot be 0, it cannot be 2 or more. It has to be exactly 1. Alright. Yeah, it's missing a comma, but that's kind of besides the point. And then Danny has a question. Do we ever use the idea of transformation in this class? This reminds you of a one-to-one transformation. I'm not really sure about what transformation exactly means in the other context, so I cannot answer that question until I can find out exactly what we mean by transformation. I'm suspecting the answer is a transformation in that context is a function, but I'm not 100% sure. Oh, okay, in linear algebra. It depends on how you define the domain and the codomain. But at first glance, if I were to just kind of intuitively guess, what the answer is, then my guess is the answer is yes. Okay, so and then Elijah asked, can you have all the elements of the domain map at least once to the same element of the codomain? Yes, that will work. So A1, B1, C1 is a function, not a problem. And then Chris said, yep, it's a function. Okay, that's just double confirming, but Chris got to it first. And then Luke said, I think he means, can elements in a codomain be mapped to by multiple codomain elements? The answer is yes. It doesn't break the rule of what we have said here, because it doesn't say anything about uniqueness in the codomain. Because all it says here is each element of the domain must be mapped to one and only one element in the codomain. It doesn't say anything about can everybody in the domain map to the same thing in the codomain. It doesn't say it's not okay to do that, because it doesn't say anything about map to unique elements in the codomain. Now, if I add the name, if I add the adjective of unique, then we cannot map to the same thing in the codomain. But since unique is not a part of the description, it is okay to map everything to the same thing. All right. Cool. All right. So the next thing we want to go through, I'm just looking at the time because what comes next is a little bit long and a little bit convoluted. But it is convoluted because I want you guys to get used to the notation that we are going to be using kind of for the rest of this semester. Alright, so however, English, like all natural languages, is not exactly precise when it comes to mathematical concepts. Just sometimes, when you are reading a sentence, just by grouping the words in a slightly different way, the sentence can mean something that's different. So that's why natural languages are inherently ambiguous. It is best, therefore, to re-express the criterion in a much more precise and concise mathematical way. We can start with examining whether to use the universal quantifier for all or the existential quantifier there exists. So I'm basically illustrating, how do you convert something from a natural language description like this, even though, yeah, I kind of get the concept, but if we want to express this, using mathematical symbols, how would we do that? So we start with, okay, let's start with a quantifier. Okay, do we start with a, universal quantifier or do we start with an existential quantifier? Because the criterion is to be applied to every element in the domain, and that is implied by the word each in the original English description, the universal quantifier is needed. If the requirement only needs to apply to at least one element, then the existential quantifier is going to be used. So in this case, we definitely want to use a universal quantifier because of the word each. So now we know the statement should look like this, okay? For all E in X, P of E, okay? Some kind of predicate P. So next, we need to figure out a way to express the predicate P. Now remember, predicate is just a function that returns a Boolean. So, it's just a fancy name for those, functions. P of E needs to express the fact that this element E maps to one and only one element in the codomain. So this is the next task that we have to handle is how do we express something like this? P of E is true if and only if E maps to one and only one element in the codomain. So this implies some kind of counting is needed. In other words, we basically can just kind of count, right? We can count, okay, let's check how many things in the codomain E is mapped to. And if that count is exactly 1, we are good. If it is not exactly 1, we are not good, right? So that means we can now kind of work on our predicate to be counting something. Remember, this is the cardinality operator. It basically says how many things are in a particular set. If the count is 1, then we are good. If the count is less than 1, we're not good. If it's greater than 1, we're also not good. So I'm working on this expression gradually, by just thinking about it, and try to pick from the toolkit of, okay, next, what do we need from the toolkit? Oh, we need to express this kind of a concept. We probably want to use that specific tool. So that's what I'm trying to do, is to kind of explain the rationale behind the final form of this expression. In other words, we are now shifting our attention to constructing a set where its cardinality counts the number of things that the element E from the domain maps to. Since E is bound to a particular element in the domain, which is X at this point, we do not need to worry about choosing which element in the domain. In other words, by the time we are working, when we're trying to work out the expression inside the parentheses, we already know that E is an element from X, so we don't have to kind of worry about that part anymore. So given that E is an element of X, how do we know what it is mapped to in Y? Since F is a subset of the Cartesian product between X and Y, each element of F has to be a mapping from one element of X to an element of Y, meaning the first item is from X, the second item is from Y. We now need a way to constrain to just elements that E maps to. So in other words, the set that we are trying to construct may look something like this. So this is a notation that says, each item in the set that we are constructing has an element that is a 2-tuple, where E is the first item of the 2-tuple, and E is coming from the universal quantifier. So we don't have to ask, where is that E coming from? Well, E is already determined by the time we get to this expression. And then we have an unbound variable called Q, which is basically saying, oh, we'll just go find, EQ, in this particular form according to what is described in the ellipses, in the ... So this constrains the element in this ad hoc set. Now, this is just my term, an ad hoc set is basically just a set where we describe its membership on the fly. Okay, it doesn't have a particular name, doesn't have a particular significance other than the current context. So it has to be a 2-tuple. Every element in this set has to be a 2-tuple, and each 2-tuple starts with the specific element of E, which is basically coming from the quantifier. We need a second constraint because we are these typo here because it's supposed to be constraint, not constrained. So we need a second constraint because we are only interested in tuples that are in F. So the set will spell out like this. So now we are specifying, okay, let's find everything, let's find all the two tuples in the form of EQ. E is coming from X, Q is basically just a variable that can bind to anything that satisfies the other requirement on this side. So the other requirement of this side is, oh, okay, EQ just has to be an element in F. So now we are basically counting, right? For each element of X, we are counting how many things in the codomain is it mapped to. So now that we have the ad hoc set constructed, we can plug it back into the quantified statement. The final answer is, for all E in X, we look at the cardinality of the set, the ad hoc set that we are constructing, and then in order to qualify as a member within this ad hoc set, it has to be a two-tuple where the first item is bound to the same E, which is bound by the universal quantifier, and then Q can be anything as long as EQ as a two-tuple is an element of F. And we are counting this because of the cardinality operator, and it has to equal to 1. So I'm looking at the time. It's 1:15. All right, so we're going to take a look at this, and we want to look at a few examples, just to find out, how this works. All right, so we got a few examples where things did not work out, those were not functions. So we can always start with those items and basically look at, okay, with those, what is this going to look like? All right, so we're going to take a look at the first one, which is this one here that is not a function. All right, so there we go. All right, so this is not a function. So what we want to do is to say when E is bound to element A, then the cardinality of the set. Oh, I should probably change this. The set where we have EQ such that Q is in F. So what is going to be this ad hoc set in this case? Let me close the thing first so it's easy to read. So if I want to know exactly what is this particular set when E is element A in X, what do you think is the spelled out version of this set over here? So that's the question. I want you guys to kind of think about it and see if you can answer the question. I'm going to press the button. Alright, so I'm going to repeat the question. So I want to answer this question over here. Knowing that E, which is a variable, is bound to element A of X, which is our domain, I want to construct the ad hoc set that satisfies this requirement. So the question is, what does it have? And I made a mistake here. This really should be EQ in F. Sorry about that. In other words, I want this spelled out membership of what is going to be inside these braces. So the question is, what should it contain? And Elijah is right. Alrighty. There you go. So do we have another person who's getting this right? Alright, cool. Alright, so I'm just gonna type it in just so that we have this complete. So we got A1 and A2 in this set. So given that is the case, okay, what is the cardinality of that? In other words, if I look at the cardinality of the set that we have just constructed, what is its cardinality? And Ansel is right. Cool, you guys are all correct. There we go. So that is indeed 2. And now we can finish the entire evaluation, which is what is the value of you got it. There we go. All right. All right, so we are technically done because I don't even need to look at B or C, because if one element of the domain is failing the requirement that we need for every single element in the domain, we know this f is not a function already. Is that okay? Does everybody kind of understand this concept here? I know we're running out of time, but I'm gonna push a little bit, and we're gonna work with the second example here. I mean, I really think it is important to kind of make sure that we understand this part here. So this time, I'm not going to look at when E equals to A. I'm going to look at it when E equals to C. I want to see what happens. Okay, so I'm going to copy the rest over here and then get rid of something that we have previously worked out. And I want you guys to give me the answer. So what is on the other side? What is on the right hand side of this equal? Yay! It is indeed the empty set. So what is the big deal of the empty set? So I'm going to copy and paste this over here, and you tell me what is supposed to be that number. What is the cardinality? Oh, okay, I got it wrong because I kept everything from earlier, but now it is an empty set. Yay! Indeed. And the next question is even simpler, because all I'm asking is this. Yep. It is false. It's false because we cannot handle the truth. Someone bring up a Jack Nicholson picture here. You can't handle the truth, and therefore this is false. Right? Okay, so this time, we found out that there's one element in exactly. So since we can find at least one element in the domain, which has elements A, B, and C, and for that one element C, the criterion that we are trying to evaluate turns out to be false. Now, since the quantifier is a universal quantifier, we need the criterion to be true for every single element in the domain. The moment we find a single element where the criterion is false, we can now say, this is not going to be a function. F is not a function because we find at least one thing in the domain where it does not meet the requirement. So are we doing okay? Because I think I'm going to stop the lecture at this point. This is a lot of stuff where when you listen to me explaining it in the class using examples, you go like, yeah, everything is gonna check out okay. I'm totally understanding. But when it's time to actually apply that stuff, it can be different. So it is important to kind of go over the material over the weekend, and see if you can come up with some examples to yourself, right? So you can just go like, okay, this is x, this is y, and this is f. Is this f a function or not? Okay, given these are the members of f. If it is not a member, why is it not a member? Is there only one reason for it not to be a member, not to be a function, or are there multiple reasons why this f is not a function? So come up with examples. Okay, come up with some examples where f is a function. It just looks a little odd. It just looks kind of like ugh, but I guess it's still a function. And then also come up with some examples where f is not a function. Okay, and come up with some examples where f is not a function for more than one reasons, and come up with examples where f is not a function because of one single reason. So all of those things are things that you can kind of exercise and just really work on it, because the more you work on this, the more you try to come up with examples for yourself to evaluate, or you can have a study group. Okay, everybody just come up with a question for everybody else, then you end up with a bunch of questions and you guys can all talk about it. So I think those are all going to be useful activities for you guys to do over the next 4 days. So I just think that might be something that you can do over the weekend. That can really kind of help, because it also helps to retain the knowledge, right? So next Monday, by the time we come back, you guys will go like, yeah, but we're still retaining everything that we talked about last Wednesday, and we're ready to stack more concepts on top of what was already talked about. Okay, I can also kind of say that the more you kind of read these notations, the more familiar you're going to get with interpreting the meaning of these notations, and that's going to help out not only right now with functions, but it's also going to help out by the time we get to relations, predicate calculus and stuff like that, because I just use these notations a lot. When I wrote my dissertation, this is a fun story. But when I wrote my dissertation, it was one gigantic proof. It was about 60 pages long. Most are using notations like this. Okay, so I would say maybe 60-70% of the pages are populated by stuff like this. My advisors looked at that and go like, Tag, you know that you have to write in English, right? In a dissertation you have to use English. Then I go like, but these notations are so much more concise and it's so much more precise. There are no two ways to interpret the same thing, and every step is logically following the previous one. What else can you ask for? Can you write this in English? I go like, then what's going to happen to the proofs? What happened to the mathematical notations that I have put into this document? You can put that into the appendix. Then I go like, but then my dissertation only has 20 pages. Just throw in some experiments and graphs and fluff it up. Yeah, that's what I did. I fluffed it up. So, okay, so there are several questions. I did my dissertation, or my PhD at UC Davis. So if you go to the physical science library in Davis, you should be able to find my dissertation. Yep, fun time, actually, fun time. Alright, well, I don't think we have anything else that requires the screen share, so I'm gonna stop the screen share, but I will still kind of be answering some questions if you guys want to. No, we will not be doing integration in this class, because integration is continuous math. It is not discrete. Don't tell your calculus professor, but that belongs to a different branch of mathematics. It is not discrete math. So what is not discrete? I'm not gonna say that, okay? But this is a pun that that can probably offend some of your calculus professors. It's like, Tech said the math that you're doing is indiscrete. It's like, no, just not discrete math, not indiscrete. Yeah, there we go. Yes, discrete structure is just a different name of discrete math. So there's no difference whatsoever. Some universities or college decides to call it discrete structure, and others would call it discrete math. But basically, they're the same thing. It's basically foundational stuff for more math-based computer science classes that you're going to have to take as upper division classes at a 4-year university. So this stuff here is not by itself a dead end. Far from that. This is just the beginning for many of your classes at a 4-year university. There you go. Alright, so I am going to stop the screen share and also the streaming, but I can stay behind and answer some of the text questions in the channel. Alright, you guys have a nice weekend. I'll see you on Monday. But if you have needs for my office hour, just kind of ping me during the office hour, and I will answer your questions then. Alright, bye bye.